Welcome to the SSA Canberra branch meeting for the May meeting. And today we'll have our speaker, Dr. Ling Nguyen from University of Sydney. Ling was a postdoc here with Francis and Alan, and currently he is a lecturer in statistics in the School of Mathematics and Statistics. And today the topic he's going to give to is functional space analysis of empathic accuracy. Before we do that, I've got to acknowledge a few countries, so let me do that. So acknowledge the custodian, traditional custodian of the Ngunnawal people and the place we have a meeting today, and or wherever you were on those people online. We shall respect to the elders from past and present. All right, Ling, it's yours.
Yeah. Thank you, Pauline, for the introduction, and thanks, Francis, for the invitation. So, so today I'm going to share, to talk about one of the applied projects that I work with my co-authors. Let me see to make sure. Okay, in the SM Starting Methodist University in Texas. So this one is on the statistical method for psychology. Okay, so let's start with the project. So the last two words in the title, empathic accuracy. So we will start with empathy. So when I say empathy is, it's very kind of like general word of like the tendency of one person to understand and share emotion with the other. And in psychology, there is a whole lot of literature on the roles of empathy in lives. Like if you have better empathy, it's also related to your relationship and also on the other cooperation and even cohesion of the society. So, I'm not here to debate what is empathy and what is not. But one particular aspect of empathy that brings in quantitative aspect is something called empathic accuracy. So empathic accuracy essentially is the ability of one person to accurately assess the thoughts and the emotion of the others. So, again, this one is an objective component of empathy. Because from the definition of empathy in the literature, people may argue that it's something very subjective. Like when I say, I empathize with you, what does it really mean, right? So, but the empathic accuracy just like bring the quantitative aspect to the very general definition. So that is the empathic accuracy. So the question now is, how can we measure empathic accuracy? Like, how do we know which one has more, how to say that, like more empathy with the other than the other people? So we have to measure that. And okay, so let's take a look at some of the very typical empathic accuracy study. So the first one I will introduce here is what we call the social EA study. So the way the study is designed is the following. Okay, now I have 4 videos, and in each video, one person, let's go to the target. They try to discuss a live event. And then at the beginning, we kind of told the target to say about, for example, like whether it's a positive or negative event, and whether the level expressing it is low or high. So there are 4 videos. So each video corresponds to one combination of what they call the valence or the overall emotion and the level of expressing it. So there are 4 videos. Okay, so that is the first part of the study. The second part is now, okay, they let each of the participants, they recruited the participant, and then they let each of them watch the video, watch each video. And then because they watch that on the computer, they can move the mouse to continuously read the target emotional states. So I will show you the data later. Essentially, Like when you watch the video, you have to do kind of like multitask. Like you hear, you see the video, the person, and also your hand. You also have to move the mouse to indicate the target emotional state. So a little bit more details in the rating is on 9-point scale, and essentially the scale just like the higher the more positive. And the data was collected every 1 second. So it's really high frequency. So the video itself is only like about 1 minute, 1 or 2 minutes, but the data was captured every 1 second, or even in the latest study, they even reduced that to like half a second. So it's really high frequency. Okay, so that is the participant one. But then the last part of the study is the target in each video. They also rewatch its own video, their own video, and then also provides such a rating. And the target rating is used as a benchmark. So it's essentially they think that, okay, the target should know exactly their emotional state in each point during the video. So, and then they use the target rating as the benchmark. Okay, so that is the social empirical. So the next study, this one is I got involved in when I was asking you as well, the music. So the similar design. The only thing that changes here is the target now is the composer. So each composer writes a completely new piece of music. And then I would like to hear one of them. And so there are 12 composers or 12 targets. And they write the music and based on some categories. And essentially, there are 4 main groups: happiness, sadness, anger, and tenderness. And after that, they do the same thing. They let each participant in the study listen to each music once and only once. And so they kind of like that they have to the participant while listening to the music also provide a rating. But the question they ask the participant is, what kind of emotion level of the composer? They don't ask the participant about what the participant feels. They ask about what the composer wants to convey, like the level of emotion want to convey. And okay, so we can take a look at one of the music in this one. So let me stop share this one, and then it's a quick music. So this one, let me see if I can. I don't know. I hope you. Oh, I don't know. Yeah. Yeah, so this is one of the music that we use in the study. So let me share the slide again. Here. Otherwise, the talk will be a concert, right? I mean, if you're listening to the music, so okay, so so here is next thing is one of the kind of data that we get. So essentially, in the plot here, the red curve, the solely one is the target rating. So this one from one of the video from the first study, and each of the dashed line is one participant rating for the video here, because this one, the low negative, only about 1 minute, about 55 seconds. So, yeah, so at each time point, every second, they capture the rating given by the target and given by each participant. So so that's the data. And the question now is how can we quantify the empathic accuracy? So essentially the idea is how can we compare the solid curve with each of the dash curve? So that is the general, questions of how can we do that. And so let's see what people do in the literature. So in the literature, when I started the project, I was surprised. The only thing that people use is sample correlation. Essentially, they only use the sample correlation, measure the correlation between the solid curve and the dash curve. And they use that as a measure of empathy. And well, here I think in statistics, we know correlation has a lot of advantages, disadvantages, right? And they only measure linear relationships, some sort of like that. And when we get into that project first, so we want to replace the correlation by some sort of linear model or even linear mixed model to make it more flexible. But after we do that, we recognize one fundamental thing in the data is the misalignment. Because when we compute the correlation, essentially, we are trying to compare the rating point-wise. So we compare the rating line here, like in the plot here, at each time point. We just compare the rating of the target and the rating of each participant. So it's a point-wise comparison. But clearly you can see the plot here. The issue is the misalignment. And the peak of the red curve, right? And then let's say the peak for the green and the blue dash curve here, like the general pattern is really the same. But the only thing that is different is the misalignment. Because, yeah. And now let's think about the design study because the target, they kind of re-watch the video, or the composer, they re-listen the music, so they know exactly what is coming up. And that's we really think that is really created by the bias, or that introduced by the fact that each participant, they only watch the video once and only once, but the target, they know what is coming already. So they can kind of adjust for that. But in general, the idea of the misalignment is people may have a different speed of perception. They don't just, here the one data, in general, like the cognitive process, like sometimes we slow, sometimes we fast compared to the other, but the overall we have to take into account the overall shift. And this one in the literature is also known as the phase variation. We just kind of have a different speed for the perception during the time. Okay, so that also brings to the comparison between how this kind of data are usually treated when we do the analysis. So when we do the point-wise comparison, like the correlation, the data essentially is a multivariate data. We treat them with multivariate, like we do the target on one axis and the participant rating on the other axis. And then after that, you compute the correlation or what kind of model. So the data itself essentially is only X and Y. But the functional data perspective, essentially, you want to treat the sampling of the TI, the time itself, as a component of the data. And we want to use the time component explicitly in modeling the data. And so, here from the theory perspective, it's kind of like the functional data analysis, we take the sampling into account. And so even if we want to, for example, like up sample or down sample the data, we have to take the GI into account as well. And from the theoretical perspective, like theory for the functional data analysis is developed on the function spaces instead of finite vectors. And but you can review that at the end of the day, right? Computer only discrete things. It's just like discrete, but the discretization step only implemented at the very, very end. And here is one quote from Fernando, like you have to discretize as late as possible. And that's so the multivariate and the functional data. And so here we redo the analysis and then we want to check the data from the functional perspective. And particularly in our context, only when you check the data as a functional data, we can model the misalignments explicitly. And then we will introduce a model for the misalignment. And here, I just use here the data will come we had like this is the target rating at each GI, it's just a function of the GI and Y similar for the YI. So this is the kind of like the motivation. We have the data, we see the misalignments. And so instead of treating the data as multivariate data, we treat that as from the functional perspective to model the misalignment. So let's see, how can we model the misalignment? Okay, so the assumption now we will have is we will have some kind of like the two target and participant ratings, X and Y. I know that as X star and X, Y star here. And then it can be a set of like functional data, like each of the time point, just a random variable. And with a lot of generality, I just like the domain of each function is on the unit interval from 0 to 1. Now, what we assume is the data has misalignment, right? So what we assume here is the concept of domain warping. So instead of observing the data at xt here, essentially our data is the two function x star, but warped at the here by the gamma 1g. So gamma 1g is kind of by the domain warping function. So actually dot t here is what we observe, but it's just like kind of like the result of some warping function inside the cognitive process for for both of the target and also each of the participant, and similar for Y. So why we observe the data YTI? So TI essentially is the function of the another warping function. So each target and each participant may have its own warping. So it's more like think about it as like how can we perceive our time, right? Because sometimes we may be really slow and sometimes we may be fast. And so the warping function, but the clock time is something, well, let's say it's universal. But like when it comes to the process, cognitive process, then we can have a different perception of that. And in terms of the mathematical language, so this is kind of like the competition of the two functions. It's a competition of x star versus some gamma 1 and y star with the gamma 2, and gamma 1 and gamma 2 are time warping function. And so what we assume here is the two observed functions, they are misaligned because the gamma 1 and gamma 2 are different. In the ideal world, there will be no misalignment, but somehow we get kind of by the function get warped, or the domain of the time get warped by the two different warping functions, and that's why they are misaligned when we observe that. So let's take a look at some of the effects of this one. So in each of the plots here, in each of the column is the solid red, solid black one is the two function x star. And then under the effect of some warping function, it can changes. So the domain is completely here. The effect is only on the t. And like under the different working function, you can see that the resulting function that we observe can be very different from the original two function. The dashed line is the result from the working here. So this is this one. Now, so that's the idea of we model the misalignment that happened in the data due to the working function. Because I mean, originally we assume that without the working function, there would not be any misalignment. Only under, because the process, the cognitive process, we have the different working function for the participant and for the target. Then we have the misalignment. So this part become a little bit technical, but essentially I will try to explain the idea. So now the question we want to do is we want to model the relationship between the two functions, x star and y star, but we only observe the what version of that, x and y. So the question is, how can we study the relationship between x star and y star from the data only the x and y? And okay, without any other assumption on the working function, it's very challenging. And so we need to put some assumption on the working process, how we assume about the working in the domain here. So like the working to me is really like how people perceive time in when it comes to the study. And so one of the common assumption is they call that the boundary preserving diffeomorphism. But in general, the idea is only like, okay, you have to start at the same point. Gamma naught, gamma 0 has to equal to 0. You have to start at 0 and then you have to end at 1. So it's a function. And then the function has to be smooth and invertible. So invertible just means that you have some inverse function, and that is unique as well. So this is the assumption on this one. And okay, then essentially, after that, now the thing that I will focus on the rest of the talk is now the strategy, right? How can we measure the empathy accuracy? So the idea is, okay, first do the alignment first. And then after that, you compute any measure of the relationship between the function that already get aligned as an estimate for the measure of the relationship between the two functions. So that's the strategy. And we hope that by doing the alignment, we should get a better measure of the empathic accuracy. It means the true relationship between the x star and y star function. Okay, now the question now is, how do we know if the two functions are aligned? Right, and again, this is a very typical example of like it's very easy to do visualization. Like you can see things, but from the computer, right? I mean, I don't like computer vision. How to make computer see that, right? Like whether you know how to some sort of like measure to know if the two functions are already aligned or not. So the idea now is, now we want to do some sort of distance function, right? Let's say you have a two function, f1 and f2, and we want a distance measure that satisfies, first of all, okay, if f1 is well aligned with f2, then f2 has to be well aligned with f1. So that is the first thing. The second property is the smaller distance is, the more aligned two functions are, right? And that, and I hope it is straightforward. And of course, when f1 and f2 are the same, then the distance has to be equal to 0. Now, but the last thing that makes it a little bit different from the other area is, okay, the distance should be invariant to the same working. Meaning that, okay, if I have a two function f1 and f2, if they are worked by the same working function gamma, the distance should be stay the same. Essentially, the idea is if f1 and f2, they are already well aligned with each other, then if I work that, by the same working function, the resulting function, you still have to be well aligned. Right? So that's the intuition of that. And then because of the last condition here, the magic, we actually measure what we call that the distance in terms of shape between the two functions. Essentially, when you align the two functions, essentially you try to make the shape as close as possible to each other. So that's why here the magic is measuring the shape between the two functions. And because of the last property here, one common magic we do have if you treat the function data again as multivariate data, if you do that by the L2 norm, it is not suitable. Because like in this example here, I have the first two functions, right? So this one is from my eye, right? And then I can compute the L2 norm is 0.44. But now I want the two functions by the same gamma. Then they are still well aligned, right? But the magic changes. And that is not desirable, right? Because how can I walk by the same function and then my measure distance, like the shape, like the relative distance in the shape should not be changed. And so one solution for that is really, recently developed in the literature is taking a look at the derivative of the function. And okay, this one I just is called the square root velocity function representation. And okay, so essentially it's a function of the derivative of the two functions. And so essentially the new distance is the L2 norm, but not on the original function, but on some kind of like function of the derivative of the two function. And but again, this one is just by the magic to do the shape analysis. And if you, from the theoretical viewpoint, it is just an extension of the Fisher-Rao magic between the two probability density. But they generalize that for the larger cases of function. Okay, so here is the demonstration here with the same two functions. So this one, the L2 norm, you see that it changes by the watt rate. But the new distance here, no matter you can change the working function into whatever form, this one will always stay the same. And that is a kind of like distance that we want to use for the aligning the two functions. Okay, so then the idea now becomes fairly straightforward on how to do the align function. So essentially, because we assume that there is invertible watt rate, and so essentially here from the data, we only have the data for X and Y, and so the thing now is I want to minimize the X what by the gamma inverse. The inverse of gamma and Y is also what by the gamma 2 inverse. And because this one due to the distance property, then it is the same as X, and then you what the second function by multiple kind of like a two combination. And here, essentially due to that, like in practice, what you only have to do is you assume one function is not what, and then you just align the other function to, like here, I can assume that X is really something like unwhat, and then Y, just like you align or you try to find the gamma function that make it close to the X as possible in terms of shape. And so here's the technical thing is the SRBF. Here you can write that in terms of the L2 norm of the square root velocity function as well. Okay, and finally, let's get into the implementation. So implementation essentially is based on not on the gradient descent or something, but it's based on something from the dynamic programming algorithm. So this one essentially, we also have to find a discretized version of the warping function gamma. And then actually they have a package in both R and Python to do that. So the observed data would be used as well. Okay, now let's take a look at here is the result. So here's one video, right? I mean, I showed you that clearly the participant waiting here is not well aligned with the target. And so essentially using the algorithm and then the package here, you can see that we can, the dashed line have a here, right? The peak is getting into the same place as well. And then here is the estimated time warping function. So it's quite a, not so nice function. But yeah, you don't really know much about like, well, but sometimes the process warping is inside our brain, and then it is what is estimated from the data. And so also is another thing here. It is the align function. Before it's not aligned, and then when we align the function using the algorithm and using the right magic, we can get it aligned on the visualization viewpoint. Okay, but that's not the end of the story. I mean, if you think about it, that kind of process really easily to overfit. And one example is the first kind of block here. So you can see that like if I use this one, right? So this one is the estimated gamma function, the warping function. And then like the align function, they get pushed a lot into the previous, like in the earlier time. And yeah, when we see that, I think, and then the psychologist essentially said, no, this is almost impossible because like this one here, originally, like this one, it's a kind of like later part of the video, but it gets pushed back by a lot, right? It gets pushed back a lot by earlier by the aligned function to get a peak here. And then after that drop, I mean, dramatically. And then it's like really not really reasonable for the cognitive process, like the way we, like the emotion we don't, I mean, I don't know if you believe it or not, it's just like you are very high and you are very low, like less than 1 second. And that's why the idea now is over alignment. So the over alignment essentially is the current warping function state is too large. So meaning that if you take a look at the estimated warping function, it go a little bit like here, and then they go up, and then go, yeah. And so it's kind of like, first of all, you squeeze it, then you stretch it, and then you can change that like arbitrarily during the video time. And that is too much. I mean, it's like the cognitive process arguably is not reasonable. And then in the literature, it's well documented that even if you have some kind of lag or reaction, it should not be no longer than 2 or 3 seconds. And so the idea is, let's do penalization, let's do regularization. So we impose a certain constraint. So essentially, we want to make sure that at each time point here, the difference between the identity warping, which is the identity function, and the estimated warping should be no larger than some rest of time. And that is the idea of we do the penalization, and this one also makes the regularization come in on that. So the question now is, if we impose this one, do we still have a lot of possible working? And in fact, it is. You can still have a lot like here. Essentially, the constraint only restrict the working function on the band, right? The two line, the two blue dashed line. And within that, you can still have many shapes of the working function. And so that's why we want to impose this kind of constraint. It has to be in some kind of bands of that one. And that's why, so this one also the regularization come in. So we want to minimize the distance, but now we impose a constraint. And of course, like the K here, like the tuning parameter, right? And so K, if K is 0, close to 0, so essentially you assume the effect of warping is very small. But if you get K get infinity or K very large, the constraint not really doing anything. And so you will obtain the unpenalized alignment. And then for this kind of optimization problem, we can use the dynamic programming algorithm, and then we just add the window constraint into that. And because of the literature here, we set the K equal to 3 based on what I showed you in the literature. And so let's take a look at this one here. So the same kind of data, and then essentially the on the left is a working function. The blue one is unpenalized, and then the brown one here is a penalized one. And so you can see that yeah, we want to avoid all of the like squeezing and then stretching like immediately right after that. So we want to make sure that the warping, if that happens, it only in the band. And then you can see as well is here on those align function, it different from the original function, but it doesn't differ too much on when in the first place. And then in both cases, that's what we see that like the slope of, the working function stay well in the band on this one. So that's the idea for the penalized alignment. And okay, and so with alignment, right? As I mentioned from the beginning, we can use the same measure. I was previously used some X, Y, but now we compute on the X and Y, the alignment function to measure the empathic accuracy. And I'm not going to show you the simulation because we actually showed that by doing the regularized warping, we can get a closer correlation. And I mean, the other measure, like the slope of the linear model, some sort of that as well. But here, when we apply to the data, what can we get? So, okay, so this is the 4 videos here. So we have 4 videos. So high negative. So high refers to the level of expressiveness, and then negative or positive is level of promotion. So we can see that in all of the plots here, the unpenalized easily lead to overfit of the correlation. Here, just like if you don't do the if you don't think that there is a what effect, so essentially you assume identity what. So essentially for this one is identity, and sometimes it is. I mean, some videos, so we see that the effect of the warping is very large. So when you do the unpenalized alignment, the correlation get inflated too much. Like in the second video, here the low negative one. And this one is actually interesting because for the low here, if you see on the right plot, the low negative and low positive, you will see a lot, the effect of the warping is quite a lot. Because here, if you compare the identity, here the median of the correlation with the identity and unpanel line, it gets inflated a lot. And similar thing for the low positive. So here, actually, the level of expressiveness in the video really affects how people perceive that, how people perceive the emotion of the subject. And so, but in every video, here the penalized wrapping version, here after you do the penalized version, then you can see that it kind of like the balance between the identity and the unpenalized. So the identity, if there is no wrapping, it makes the correlation artificially low. The unpenalized alignment makes the correlation artificially high. And so what we propose is the penalized version of the alignment. So it's kind of something always in between. So this one, the box plot for the distribution, but also we can see that in the scatter plot. So on each of the axis is the identity wrapping. And then the red one represent unpenalized, and then the blue one is the penalized correlation. Like the correlation after penalized wrapping. And something like the here, the low positive, the dashed line 45-degree line. So the low positive, you can see the unpenalized wrapping inflate the correlation a lot. So a lot of time it's only about point like this one, 0.6 or 0.7, but you can get into like, even this one, right? Line here, the correlation of zoom identity wrapping is only like 0.25, but it gets inflated into like almost 1. So it's just like overfit a lot. And so the panel line alignment that we propose, we will argue that it is should be the better measure for the and more reasonable for the empathic accuracy. So this is the from what we in the simulation and also the real data. So ignoring the time wrapping make the correlation artificially low, but unpenalized make artificially high. And so the penalized alignment will create a balance between that, and it's more reasonable measure, at least from the like if we stick with the correlation. But now that can be expanded even further. The more framework is we can use the idea of the working function to build more complex model. And then, so in the music study, I mean, I didn't show you the result because essentially, because now you can assume for the random effect as well. So a participant respond to more than one singular target, like they have 4 videos in happy, 4 videos in like 10 minutes. And so we can have some kind of random effect we want to account as well. And so essentially the idea now is in the model now, we make sure that we want to take into account the working as well. So, and then all of the other components, it is very similar to a linear mixed effect model. You have a fixed effect, alpha, beta, fixed slope, fixed intercept, and random slope, random intercept, and then the random noise. And so the big thing of that model can be done iteratively. So essentially, first of all, you do the alignment. Then you pick the mixed model, and then you do that again until conversion. And so I don't think I have the time to show you the result, but essentially this kind of framework on the SRVF and then the working function can be incorporated into a larger like model. Right? You don't have to do the alignment as one pre-processing and then you do the model, but we can do that simultaneously in the same when you model the functional data when misalignment can happen as well. So, okay, so again, misalignment, again, they arise naturally in the cognitive process, and but it's necessary to take into account when we do statistical analysis, and regularization, even for alignment, is necessary to overline, overfitting, and in that case, it's the over-alignment. And again, the idea of alignment is when you try to compare the shape of the two observed function. So that is an example of what they call statistical shape analysis. And so, which is, really rapid growing subfield. There are a lot of papers are doing even like the theoretical work on even application on that. So the philosophy is like, okay, the data have shape has some meaning, and meaning bring information and bring the value for the statistical analysis. And so I think it is here by taking into account the shape of the two observed function, we can measure better the empathic accuracy, and then understand the cognitive process better in perceiving social and human. So thank you all for listening, and I'm happy to take questions.
Okay, we'll start with the question from the audience first, and we'll move to the online people. So hold off your questions, or you can use your time to type. We have Francis read out those questions for us later. So let's first, yes, Robert.
I was going to ask about that SRBF alignment function. Is there another break solution for that? Without constraints?
No, there is no algebra solution. So the algorithm is the dynamic profiling algorithm. So essentially they have to, no, there is no closed form solution for that problem, and then you have to view like the optimization as like over the graph, and then make sure the cost function is like additive, and so on.
So you have to
it's a discrete diversion, and so that's why the estimated here is like a discrete diversion. I mean, you can smooth that even further, but it is the discrete diversion.
And I wanted to ask as well, does that SRBF generalize to 2 and 3 dimensions if you wanted to do?
Yeah, they do. Yeah, essentially they can. The SRBF here, it's a 2 or 3 dimensional, because they also do something on the statistical shape analysis, like when you have cloud data. So it's a more than one. So functional is just like 1D, right? You have G, and then you only have the MG, the 1D. So, but in the shape data analysis, they do have a generalization of the SRBF.
Is that the computation this problem when you work on this project?
Yeah. So this one is, the SRBF, the dynamic programming algorithm is very fast. At least for the package SRBF, they code everything in C++. So it's very fast as well. So I think the computational complexity is like, I think it's OT. So it's not true computational demanding.
More from the audience? If not,
There's nothing online at the moment.
Well,
that function though, that QT function, it's really just like looking at the length. It's the equation for the length following the length of the curve.
Yeah. It's more like the derivative, but the difference between
But that formula, the square root of the derivative, it's something we learned in the algebra. It's just measuring
the distance.
It's measuring a piecewise distance.
Yeah. So the nice thing about this form is essentially if you put in the right representation of the function, because there is I think given not really but almost like one-to-one relationship between the X and the Q. So Q is just like the SRBF. And so the idea is like, you cannot do the L2 norm between the length, between the original representation, but you can do the difference in the length in the other representation.
I'm wondering, what if I'm fast to respond to happy feelings, but slow to respond to sad feelings? In your model?
Oh, yeah. This one is on the estimate gamma function here. So let me show you this. So let's say this one is unparalleled. So this kind of here, right, is given like how you fast when the water is very flat. You just like you stay at one particular time point, and then you stretch that. So it's kind of like you kind of like slow motion, right? When this one, but when you get into something heavy like this one, you get very stiff. Then it's just like you can fast forward to the future, and then so that's the idea of slow or fast. And then but we want this kind of behavior can change from time to time, but it's, as long as it doesn't change too crazy from one time point to the next time point.
I guess the idea is that you want to align.
Yeah.
You're just aligning the wrong upticks.
Right. So, the unpanel line here, essentially they align this point with this point. So, but it's kind of like, to me, it's really two different parts of the video, and it may not reasonable to align this thing like that.
Yeah, I mean, sorry, I'll follow up sort of with Robert's question, which is obviously like the capital K itself. I mean, in a sense, that kind of also has a meaning, because you say it's 3 seconds, but you're saying that basically everybody has to respond within the 3-second window of the target.
Yeah.
So, I mean, in a sense, well, I guess my comment was like, okay, well, in some sense, you almost want to try to choose that in a way, either based on some very strong prior knowledge, which you did.
Yeah.
But also, you presumably it also like it would differ for different individuals, and it also potentially differ for different types of music, which is or what you were saying.
But sometimes like different individual can have a different like if they already are into like the first one here. I don't show it here, but the K doesn't really have a lot of influence, because if you were like here, it's like 1 second or something like that. You only need that. So the K doesn't, the threshold doesn't really play any role at all. But some individuals that play a big role. So you're right. So it can change from one individual to another.
The issue is really just making sure the bumps line you're responding to the correct bump. So if they had another bump, you wouldn't want to align that bump to the other example was better to showing that. Trying to align
the other
the fitted example, it's that big increase, it's lined it up to the big increase. Right? So that
I think there is like, I think there is some kind of like level whereby it doesn't affect it that much, but it also something is, because in some sense it kind of does have a meaning, in a sense of like saying 30 seconds is saying is kind of like a maximum kind of.
Right. I mean, so that's also, we also think about like we can actually measure the like the optimization problem here. So like you can use the minimum like at the gamma half, right? You can see the let's say I can see the objective value of the optimized problem. And some people even call that, like if you here gamma half, that L gamma is called the phase distance, like the phase distance between the two functions. And whether, it's like the two observations two curves can have just like a different phase.
Sorry, there is a question in the chat. Why do you think the self-assessment of the person producing the text code is a good baseline?
Okay, let's see. Well, I mean, Okay, that is so that is in the video. Okay, so in the video, so this one is in the literature. It's not the first one I got, but it is like they say that because when you talk about that, like, and then you rewatch that, so you kind of maybe you may know what you really feel when you get to that, when you talk about that. Okay, but the music one is actually interesting because actually what we think about the music is like maybe the composer rating is not really reliable, but we can really get into, like, for example, you can get into the sound file and then you decompose all of the section of the music, like, for example, like the rhythm, like where the changes, and so we can see like participant, what kind of component of the music they are really responding to. Do they really respond to the changes in the rhythm, or do they really respond to the changes in like tempo or everything like that? And so that kind of like, that can possibly remove the bias introduced by the fact that like maybe the composer or the target doesn't really know what they want to convey, right?